Happy Wednesday, everyone. My name is Yilin Zhuang. I'm the Water Resources Regional Specialized Agent in University of Florida, IFAS Extension. Welcome to the Water Wednesdays. Water Wednesdays is a webinar series about Florida's precious resource, water. Every Wednesday afternoon at 2 o'clock Eastern Time, we will live stream a talk about Florida's water and what we can do to protect it. And for last several months, we've been live streaming this talk on Facebook. Some of you have expressed interest in attending the Zoom webinar directly. As you asked, we listened. Starting this week, you can register our Water Wednesdays and interact with the speakers on Zoom directly. And this month will focus on Florida springs. And today I invited my colleague, Dr. Andrea Alberton, the Northwest District Water RSA, to give us a talk about Florida spring, especially its water quality and effect on algal blooms. So let's welcome Dr. Alberton.
Thank you, Yilin. Yilin, should I go ahead and share my screen?
Yes, go ahead.
It's somehow it's saying I can't share it. Okay, here, hold on. Sorry, everyone, it'll just take me a little while. Can everyone see my screen? Can you see my screen?
Yes, we can see it.
Okay, so once again, thank you all for logging in, and thanks, Yilin, for inviting me to speak at your Water Wednesday. As Yilin mentioned, I'm the Regional Water Resources Agent for the Florida Panhandle, and I'm excited to talk to you about Florida springs, particularly water quality and relationships to algal blooms. This is something that I looked at during my graduate study while I was at the University of Florida. So let's get right into it. So anytime we're talking about springs, we really need to start with the Floridan aquifer system, which is the real reason why we have so many springs in Florida. So the Floridan aquifer system is one of the most productive aquifers in the world. It encompasses an area of about 100,000 square miles. It's huge, and it reaches all the way into South Carolina, Georgia, and to the west into Alabama. It supplies drinking water to more than 11 million people in Florida. So it's hugely important to our well-being, actually. Aquifers are layers of porous rock, such as limestone, rock fissures, unconsolidated material as well, like loose material like sands and clays, that have the ability to hold water and to transmit water. And what this map shows here, it's a map from the United States Geological Survey, and it really shows aquifer transmissivity, which is how easily an aquifer conveys or moves water. So darker areas are shown on the map. These are areas where water moves more easily through the aquifer in features such as springs and sinkholes, conduits, underwater streams. And these are also areas, the darker areas, where wells tend to have higher yields. So there seems to be a lag. There we go. So Florida has one of the highest concentrations of freshwater springs in the world. It's amazing. Here I've shown you 4 examples. Maybe some of you have already visited these springs. There are found some of our larger springs throughout the state. We have Madison Blue Springs in North Florida in the Panhandle area, Jefferson County, Alexander Springs in the Ocala National Forest. Weeki Wachee is in the southwest portion of the state, and then Little River Springs down here at the bottom right. That's along the Swanee River. So just 4 examples of the more than 1,000 freshwater springs that are found here in Florida. These are the larger ones. So why do we have so many springs in Florida? And it really has to do with our geology. So what you're seeing here is a cutout. It's a diagram of what the aquifer, down here in gray, this area, looks like. This is an example of what it looks like in the Swanee River Basin. So basically, Florida is underlain by thick layers, represented here in gray, of limestone, which is calcium carbonate, and dolomite, which is calcium magnesium carbonate. So as rainwater seeps through the ground, rainwater is slightly acidic. It ends up dissolving the limestone and the dolomite, and that results in the formation of sinkholes, springs that we see over here, underground conduits, fissures, caverns, just a whole lot of ways that water can move into and out of the aquifer. You can see from the slide that there's a very strong connection between what goes on above ground, our land use activities, and water quality in the aquifer. So in areas that are unconfined, I've marked this here in the center of the screen, I have it with an arrow. In areas that are unconfined, the aquifer is more vulnerable to contamination due to land use activities. And in these areas, the upper layers, it's shown here as undifferentiated sands and clays. It consists of these sands and clays or more loose material that water and other things can more easily percolate through. So we have a lot of recharge in this area. Say rainfall comes down through and can more easily move directly into the aquifer. And that's why these areas are more vulnerable. In contrast, we have other portions of the aquifer with confining layers. You can see that over here on the right-hand side. And what that means is that the aquifer directly below a confining unit is less vulnerable to contamination. Confining units tend to be things like thick layers of fine clays. So think of a hard pan layer or rock and clay formation. So things that keep the water from percolating directly down into the aquifer. The water ends up finding its way to the aquifer. It'll flow along confining units and then find fissures and things like that to get into the aquifer. But in areas immediately under these confining units, the aquifer is less vulnerable to contamination from above ground above ground land use. This is an example I mentioned before of the Swanee River Basin. So in these areas, we have a lot of agriculture, dairy farms, things like that. We have other portions of the state where land use is more urban. So we have other sources of nutrients and contaminants into the aquifer, just depending on the land use of the areas above it. So getting into water quality in Florida springs, in about the 1980s and 1990s, people started noticing, it was more anecdotal evidence, that there was strong degradation in these springs. And what was really visually impactful was there was this increase in algal blooms in the springs. And here I have a picture of Silver Glen Springs in the Ocala National Forest, and you can see these large benthic mats, algal mats that were forming at the bottom of the springs and floating up. And these aren't single-celled algae, these are long filamentous algae. Algae that you're looking at here is formerly known as Lingbia woolii. It's now known as Microcera woolii. They reclassified it. But people started noticing more and more that there were these algal blooms in springs. I mentioned that was anecdotal largely because there weren't very many studies that were looking at the increase in blooms in springs. But we do have records that show this pictographic evidence. So at Weeki Wachee Springs, if any of you have been, there's an underwater amphitheater with a plexiglass in front, and you can watch a mermaid show. And since they've been giving these shows as early as the 1950s, we have pictures of what it looked like. So these are typical pictures of what we consider a healthy spring ecosystem. So you can see that there's a lot of submerged aquatic vegetation, this eelgrass over here on the left-hand side. You see areas in this upper picture towards the right where you can see the bottom, the spring bottom, and you do have algae in the background of these two pictures on the right-hand side. You see algae, but there's a balance in the system. There's aquatic vegetation, there's algae, sandy bottom, lots of fish, etc. This is what we consider typically to be a very healthy spring ecosystem. And I'll let you contrast this pictographically through photographs to what Weeki Wachee looked at in 2001. This was the Mermaid Show in 2001. And the larger picture in the background was taken just right outside the Mermaid Theater in 2006 when we were sampling there. So this is an area that didn't get cleared out to give the Mermaid Show. And so you can really see how those benthic mats were just increasing and starting to grow more and really taking over. Now, at the same time, really, there weren't only changes in terms of algal mats, but those were probably the most shocking to see. The same time, over a span of 50 years back, really, we were seeing reductions in discharge or reduced flows from Florida springs. There was an increase not only in algae, but also in invasive aquatic plants, like hydrilla is a good example of one that most people know. At the same time, there was a decrease in native vascular plants, that eelgrass, that submerged aquatic vegetation that I showed you in the previous pictures. And there were also changes going on in fish and invertebrate communities. But I'm going to focus really this talk on the algae, and that was what was most prominent in people's minds because it was visually probably the easiest thing to notice. So why do we worry about algal mats? What are some problems that can result with just this increased growth of these thick filamentous, so they form long filaments of these mats? So I'll start with the upper left picture, up here, where you see that eelgrass poking through, and it's completely surrounded by a thick benthic mat of Microcera woolii. And so what algae can do is it can outcompete aquatic vegetation and ends up either growing in these thick mats, or we also have epiphytic algae that attaches to the leaves of this, and it outcompetes the vegetation. It outcompetes it for light. So basically the native aquatic vegetation gets smothered. And this can have detrimental effects for herbivores. Over here you see a manatee. That's actually a picture taken when we were sampling at Manatee Springs. And there used to be a large population of eelgrass there. Now, algae wasn't the only reason that the eelgrass was gone. I think people also affected that. But you can see that animals that were used to coming into the springs to feed off of this native aquatic vegetation and calve, actually in the winter, having a harder time in many of these systems of finding that eelgrass. And so there were shifts in aquatic in the ecological community. Some of these lower pictures over here of the lower left-hand side. Another problem is just aesthetics. This is a picture of Guranato Springs off of the Swanee River. You can see the Swanee River in the background. And these mats are just visually not appealing, and they're not pleasant to swim through. And we'll remember that Florida springs are just really important recreational sites in Florida. So also the aesthetics are just absolutely not appealing. Another thing too that I wanted to show you in these pictures is that with all of these benthic algal mats, or these floating mats, they eventually decompose. And bacteria that decompose this organic matter when it dies, they require oxygen. So if you have a lot of organic matter buildup, if these mats die off, then the bacteria use up much of the oxygen, and it can cause oxygen depletion in the water, particularly in areas of low flow, which you're seeing in this picture. And then finally, on the lower, over here, on the lower right-hand side, is again that Lingbia woolii, the Microcera woolii. And what it causes, people can have allergic reactions to this. It causes something called swimmer's itch. So those are some of the problems that we see with algal mats proliferating in Florida springs. At the same time that we were seeing these increases in algal blooms and other things, there was a marked increase in nitrate levels in the Floridan aquifer. And what I'm showing you here is nitrogen concentrations and phosphorus concentrations through time at Weeki Wachee Springs and Silver Springs. The USGS has good records. They monitor many of Florida's springs. These are just two examples, but the trend was similar throughout the state, where here in red, if you look over time, concentrations of nitrogen in the nitrate form increased dramatically from 1970 up through 2000, whereas phosphorus concentrations stayed basically the same. The same thing occurred in Silver Springs. Nitrate concentrations increased while phosphorus concentrations basically stayed the same. And that led to the obvious question that was on people's minds of, is the increase in algal biomass that we're seeing in these springs a direct consequence of increased nitrate levels in the Floridan aquifer? So the Florida Springs Initiative, which was started by DEP in 2001, funded a study that was a collaboration between Michigan State University and University of Florida. And I'm talking about this one because I was a part of this study. I was a part of the second phase, which was in 2005 to 2008. And basically the question that we were looking at, the primary one was, is there a direct relationship between algae and water nitrogen concentrations and phosphorus concentrations? We studied many other things, but really that was the main gist of what we wanted to get at. And so in both phases, we conducted field surveys and laboratory studies to get at those questions. So what did we find? Basically, the major studies of these years was that there was macroalgae at all sites. So we studied 28 first magnitude and second magnitude springs. These are larger springs. First magnitude springs have flows of over 100 cubic feet per second. And on top of these 28 sites, we also studied had transects in the river run. So when springs come up and the water flows out, they form these beautiful crystalline rivers. And so we also looked at sites downriver at multiple springs. And what we found was that the most common species of algae, and I've shown you pictures here, is that Microcera woolii and Vaucheria species, which is a yellow-green algae. But we did not find that silver bullet. We didn't find a clear relationship between nitrogen concentrations, which is or phosphorus concentrations in the water, and algal cover and thickness. So what you would find, or what you would have expected to find, was yes, in springs with high nutrient concentrations, we'd have more algal biomass, more percent cover of the area. And in springs with very low nutrient concentrations, we expected to find lower biomass, lower algal biomass. But I'll show you what I mean by we did not find clear relationships, and I'll explain these next graphs. So in both phases of the study, these were typical findings. So what this is I'm showing you Microcera or Lingbia percent cover. So in the spring boil area or the head springs area, or if it's transit downstream, the percent cover, how much of that area is covered by Lingbia on the y-axis, this vertical axis, as compared to total nitrogen concentrations in milligrams per liter. So as you can see, what these blue dots show are sites, and this red line is our trend line. So basically, what I'm showing you here is that in springs with very low nutrient concentrations, say near 0.1 milligrams per liter, which is low, we had sites with very low percent cover, but we had also sites, if you go straight up, with up to 80% algal cover. And we also had springs with much higher nutrient concentrations, getting towards 5 and 6 milligrams per liter, with very low algal cover. The same relationship was true for total phosphorus. You have springs here in blue are spring sites, these points with very low nutrient concentrations, but very high algal percent cover in biomass. So we had hoped to find a direct line, where you had low nutrient concentrations, low algal biomass, high nutrient concentrations, high algal biomass, but we just didn't find that. So really what this was indicating was that the relationship in terms of water quality, and here I'm really talking about nutrient concentrations in springs, is a much more difficult one to parse out. We don't have a simple answer for it. So other studies have looked at this as well, right? And other research findings out there indicate, there was a big study actually that was recently finished in 2017, the CRISPS study, that was funded by the St. John River Water Management District, and many people at UF worked on that looked very intensely at Silver River, and it looked at the Alexander Springs Creek as well. And some other studies that found sort of similar findings. So the CRISPS study in Silver Springs also found that productivity or plant growth doesn't appear to be limited by nitrogen. So reductions in nitrate alone aren't likely to restore these plant communities, to decrease the concentrations of algae there. Studies that I conducted when I was a graduate student, when our group and others conducted lab studies, did show, however, that a reduction in growth rate, so how quickly these mats grow, we did see a reduction under lower nitrate concentrations. Now, these again were in greenhouses and in lab studies, but the idea here being that maybe reduced concentrations might reduce growth rates. Another really important finding from the CRISPS study was that flow velocity is important to slough off algae. And what I mean by this is that we were looking at nutrient concentrations always, but what we're realizing is that flow and how much volume and the velocity of water that comes out of these springs is really important. So when flow is reduced, algae tends to sit around. So at higher flow rates, the algae, if you think of these thick mats or epiphytic algae that's growing off of these leaves, that's using the leaves as a perch, flow sort of scours that off and reduces algal biomass in many areas. Other interesting work by Dina Leibowitz that was then also further looked at in the CRISPS study had to do with the grazing community. So when I'm talking about a grazing community, I mean snails, things like that. So what they found was that in areas where you had high concentrations of grazers and other invertebrates, you tended to have lower algal biomass. And the hypothesis there is that low oxygen, so let me reword that. So basically in areas, so it's a relationship between snails and the grazing community, oxygen concentrations in Florida springs, and algal biomass. So in areas where we have low oxygen concentrations in the water, tend to see reduced grazing communities, and then you tend to have more algae there. And the reason why we have lower oxygen concentrations in some of these areas is if older aquifer water is used. So if you think about it in periods of drought, or if a lot of the newly recharged water, which is really high in oxygen, isn't there, the aquifer draws from older water stored, which tends to be lower in oxygen. So if older water is coming up into these springs, many in the grazer community die off. They're sensitive to low oxygen conditions, and then the algae tends to accumulate. So basically what I'm trying to show here is that the relationships, they're just much more complex in springs than just that nutrient algal bloom relationship. Another thing too that was brought up in the CRISPS study and studies that we looked at is really that downstream effects are important. So what I mean by this is that even though there isn't this direct relationship between nutrient concentration and algal blooms in the springs, we do have to remember that the algal biomass is going downstream and decomposing somewhere, and that results in minerals that are there and nutrients that are there, and also increased levels in these waters. These spring-fed rivers many times flow into larger rivers and then ultimately to the coast. And so these increased nutrient levels may also be affecting downstream ecosystems. And finally, I did want to mention that springs restoration plans that are set up by FDEP don't only focus on algae, right? They do focus on the aquatic community and aquatic degradation. And in some of these cases, nitrogen has been found to be detrimental to certain groups, certain invertebrates, et cetera. So it's just looking at it in a much more holistic way. We started off thinking, yeah, algae and nutrients causing algae, and now we're realizing that a lot more study is needed, and that the problem is much more complex, I think, than we originally imagined. Another important finding is that you can't generalize springs as a whole. You really have to look at each spring on a more individual level. because they are completely different systems. They behave differently and they have unique characteristics and unique land use and areas around them, unique community compositions, etc. So I wanted to let you all know, many of you probably already know, but because of the degradation that that people were seeing in Florida Springs, the 2016 Florida Water Bill created the Florida Springs and Aquifer Protection Act. And so what this did was it created a whole new category of protected waters in the state, which are these outstanding Florida springs. These are the historic first magnitude springs. We have 30 of them. And these are springs that just have huge flows. So greater than or equal to about 100 cubic feet per second, which is about 64 million gallons per day. And what the state found was that 24 out of 30 outstanding Florida springs have really high nitrogen concentrations, much higher than background levels of what they used to have. And they have been identified as nitrogen impaired. And as a result, basin management action plans, or BMAPs, were developed for 13 Florida springs and spring sheds. And to date, of these 13 outstanding Florida Springs BMAPs, which I've shown here on the map, I've actually showed all BMAPs, but the Florida Springs ones are really ones here in the Central and North Florida. 8 of these basin management action plans, which are looking at reducing nutrient concentrations and restoring springs, 8 are fully in effect, and the ones that I have highlighted in light green and have blue, well, DEP highlighted them actually, and I just put blue dots on them, are currently being challenged in the courts, and so they're not fully in effect yet. But that really does end my talk. It was just a brief overview. I wanted to let you all know about springs and how they're formed and some of the problems that we're facing, and just drive home the point that we didn't find that silver bullet. It's not just because of nitrogen that we have these increased algal blooms. It's a much more complex problem, and people are doing more and more studies. So with that, I would be happy to take any questions.
Great. Thank you, Andrea. That's very interesting. If you have any questions, you can just leave in the chat box. And if you are our Facebook attendees, we all know there are about 10 seconds delay. So you probably just hear the finish of our presentation. So just leave your question on the comment section and I will read to Andrea. While you are typing your question, I do have a question for Andrea. You mentioned that it's just older water has a lower dissolved oxygen. I think some of people are wondering what is older water and what is newer water?
Yeah, that's a good question. So in the Floridan aquifer, I mean, we have the Floridan aquifer is this thick layer. And so if you think about recharge into the aquifer, you have rainfall, and so the age of that water that is in that whole system really varies, and it's hard to age it. You can have water that is thousands of years old in the lower levels, or you can have water in the upper levels that are just days old. And that's why karst topography is so complex. And you have recharge areas, particularly in the unconfined portions of the aquifer, where rain comes in and it's being mixed with water that has already been there. In times of drought, the aquifer levels aren't as close to the surface, really. And so we don't have that incoming rain, which is usually bringing highly oxygenated water into the aquifer. We're really drawing from older, deeper water that is lower in oxygen concentrations, because newer water, or water that's in streams and rivers, get a lot of oxygen from mixing with the air through diffusion or because of plants that are producing dissolved oxygen. But that older water deep down in there, really it's not getting any new oxygen infused into it, and respiration is happening. So actually oxygen is being depleted. So in times of drought, that's what we see coming up. So the concentrations of oxygen in these older waters tend to be lower than water that was recently recharged and was, in the presence of air. whereas this older water just wasn't.
Yeah, you can tell for Florida Springs. So just like Andrea said, it's a very complicated system and it's very different from like lakes and the ponds. The dynamic, it's a very different. Let me check our Facebook, see if we have any questions on our Facebook. I don't see any questions here. I think you covered everything.
Well, that sounds good. Thanks. It was a really brief overview. There's a lot more complex, but yeah.
Yeah, it is a very complicated system. It's that you can see a lot of studies and a lot of projects are going around the Florida Springs. So like I said, this month we'll focus on spring, and this is just the beginning of this month. And I will post more videos. And the next week it will be the talk is. I forgot the name. Oh, it's the economic value of Florida Springs, because we know Florida has the largest concentration of springs. So what's the economic value of that? So just stay tuned, and you can find the registered link on my Facebook page, and you can join us on Zoom directly, so you can interact with our speakers. And before I end today's webinar, I do want to encourage you to take our surveys. I post also on the chat box. So it's a very short survey, but it can help us to identify which part we've done is really good, which part we can improve. So we will really appreciate if you can take the survey for us. So thank you for your time, and thank you, Andrea, for your informative talk. And we will see you next Wednesday. Bye now.